Welcome to General Physics B2. Today we're going to talk about electric current. Let's get started. So this is the today's content, what you're going to learn today. We need to be able to describe electric current in terms of flow, electronic charge, to describe the relation between electric current, voltage, and resistance using Ohm's law. So we're going to look at Ohm's law. About conduction mechanisms in different materials, especially metals, to calculate electronic power, about electrical safety. This is also very important, so I want to emphasize this last part. Let's get started. Electric current. Electric current is a net flow of electric charge. Quantitatively, current is the rate at which charge crosses a given area. So this charge, either negative or positive, crosses the net area. This is electronic current. For steady current, the current I is delta Q, the how much charge passed through a unit time is the current, electronic current. When current varies with time, its instantaneous value is given by I equals dq dt. It's the same thing, just this is a short amount of time. The direction of the current corresponds to the direction of flow of the positive charges. So which way positive charge goes decides which way the current is running. So in this figure, positive charge is moving towards right? So current is going towards right. If negative electrons are moving towards left, then current is going to the right. The SI unit of current is the ampere A, and this is equal to 1 coulomb of the charge per second. Okay. The example B, let's also take a look at example B. If both charges, plus and minus, are moving towards right, there's no net current because the net current charges are zero. Net charges through given area is zero. So in this case, this no net current. Okay, drift velocity. In terms of microscopic properties, the current through a cross-sectional area A is MAQBD. N is the number of the charge carried per unit volume, each Watt charge Q. So N times charge Q through area A, and BD is drift velocity, or average velocity of the charge carries along the direction of the current. So this is the velocity of the current. So charge carriers may be positive or negative, in which case the drift velocity is parallel or anti-parallel to the current respectively. So this makes sense, right? Because this is velocity. So unit velocity, how many charges of Q are going through area A. So that should decide the current. That's follow the definition of the electronic current. Okay, let's look at this figure. So in this figure, these positive charges are going towards right. So the current is going which way? To the right? And then net area is A. So in this case, how many charges with area A, with the length A, and it will charge Q. So that is a charge, and that decides the current. Current density. Current density J is the current per unit area. Unlike current itself, current density is a vector quantity. So which direction is a vector direction? Current density may vary with position in both direction and magnitude. In general, the current through an area is the flux of the current density over the area. So that, of course, this is current density, right? So if you multiply or integrate by area, then you get the total current. When the current density is uniform and perpendicular to the flat area, current becomes the product of the current density with area. So I equal density times area is the current. If the current density J is uniform and perpendicular. Otherwise, you have to integrate. Conduction mechanism. conduction occurs differently in different types of materials. In metallic conductors, current is carried by free electrons. So in metal, like metals, like this table, then there are free electrons in metals. So electrons can carry the charges. Current carry the current. In ionic solutions, current is carried by positive and negative ions. So ionic solution, there are positive ions and electrons floating in a solution. So both positive ions and negative ions can move around. So both of them can carry the current. Plasma is also the same. Plasma ionized gases. So there's also ions, positive and negative. So then those things can carry the current. Semiconductors are a little bit different. Semiconductors involve current carried by both electrons and holes. Holds the absence of electrons in a crystal structure. So for example, this is a model of a semiconductor, and then there are those positive charges and electrons can move, but there are also holes where electrons can fit. And instead of electrons move, so if this electrons can fit here, but it's empty now, and these holes can move. For example, if electrons move, this electron move here, holes can move here, and this hole can move. And these are the semiconductors. Semiconductors are at the heart of modern electronics, so that camera or this computer, all of these have semiconductors. The electronic properties can be altered by the controlled addition of small amounts of impurities. So to make these holes, we need to add different molecules, different ions. Then these properties of holes can be controlled or changed. So that's how you make semiconductors that you would like. Superconductors, maybe you have heard of that, offer zero resistance to the flow of current and thus can transmit electric power without loss of energy. Sounds very good. But non-superconducting materials all require temperatures far below typical temperatures. So, like all these materials, including metallic conductors, they have resistance. So when you transmit the current or electricity through these materials, you lose some power. But superconductors, they have zero resistance. So you don't lose power and you can transmit it. So if you make these things very, very cold, and at some point they lose the resistance and they become superconductor. That's very nice. But then the temperature, almost zero temperature, at minus 273 degrees, that's very difficult to create or control. So it'd be nice to make superconductors in our temperature, but it's been difficult. So. Conduction in metals. A metal contains a sea of free electrons. So in metals, inside there are a lot of free electrons. Irons, copper, gold, silver, those are metals, and then inside they contain free electrons. They confine to the metal but not attracted to individual atoms, so they can freely. So this is a schematic view graph of a metal. Then electrons are not bound to any of these positive charges, so electrons can freely move around. So these are metals. Then electrons move about in random directions with high thermal velocities. On average, there's no current associated with the thermal motion. So thermal motion is just random motion, not in any particular direction. So it doesn't carry the current because the net movement is there. Applying an electric field superposes a small drift velocity on the electronic motion. All electrons share the drift velocity, so it results in a current. So if you put the voltage in here or electronic field here, then free electrons of course moves according to the electronic field. Then if electrons moves, minus charges move, so that creates a current. So in a circuit we have copper lines, right? So that's one of the examples of the metal. And because they are free electron, resistance is very low, so it's a very good material to make a circuit. Ohm's law, microscopic view. Electrons frequently collide with ions in the metal's crystal structure, giving up energy. The result is an average drift velocity proportional to the applied electric field. Therefore, the current density is proportional to the field. So current density, J, is sigma and electronic field. So if you put electronic field or voltage here, then there will be some current. This expression is a microscopic form of Ohm's law, and then here sigma is the conductivity of the material. So this sigma depends on material, what kind of material. The reciprocal of conductivity is resistivity. So inverse of the conductivity is resistivity. Rho equals 1 over sigma. These SI units of rho are ohm times meter. So this is a resistivity. Okay, so here's the resistivities, and then for various materials, let's look at some metallic conductors, something like aluminum, copper, gold, iron, mercury, silver, and as you can see, resistivity is very low because they are free electrons and they are free to move. So resistivity is very, very small. This is why we use those copper lines for the circuit, right? Ionic solutions. Ionic solutions is, for example, salt water. Then salt water is here. Then it's still relatively low, 10 to the minus 4, 10 to the minus 4. Salt water, the current can run salt water very easily because resistivity is relatively low. Water is neutral, right? Almost neutral, so resistivity kind of high. So in water, it's difficult to make the current go through water. Human blood is about 0.7. Seawater is lower, 0.2. And semiconductors, well, it depends on how you make it, but something like 0.5, silicon is 3. Then these insulators, the resistivity very large. So that's why they can keep charges. But by the way, 10 to 14 to 10 to the 16 watt is very, and also glass is also very high resistivity. So it's very difficult to get the current through these materials, insulators. Okay, Ohm's law continued. The microscopic version of Ohm's law relates the current density at a point in a conductor to the electric field at that point. So the current density is E divided by rho resistivity. Or instead of rho, you can multiply sigma. It's the same thing. Apply the microscopic version of Ohm's law to a piece of conducting material gives a macroscopic version. So current, if you remember, is the current density times area. And then now this J, current density, is E divided by rho, so EA divided by rho. And then now the E, you can write it in terms of this E is B divided by L, right? So, okay, then you move A here, and then it can be written that B over R, if you replace R, is rho L divided A. So you can, in the end, you can write I, current, is voltage divided by R. And then here, R is a resistance. Resistance, by definition, is this. By the way, this is definition of A area and N. So this is macroscopic Ohm's law. This macroscopic version of Ohm's law is voltage equals IR. I, current, and R, resistance. This is a relation between the current and then voltage and then resistance R. For a piece of material with uniform cross-section, the resistance flows from the resistivity, length, and area of the material. So resistance is rho resistivity times L length divided by A. That makes sense. So this relates the resistivity to the resistance. Both the macroscopic and microscopic version of Ohm's law these are empirical relations. Please pay attention to that. These are not fundamental laws like Gauss's law. These are empirical relations. So we found Mr. Ohm found this relation. Okay, Ohm's law. Let's compare the microscopic and macroscopic versions of Ohm's law. So we have the electronic field E. This is microscopic, and then if you in a macroscopic, it's going to be voltage, right? And then the relation is something like this. Voltage is E electron field times length, and then it becomes voltage. So this is a relation. By multiplying the length, you can relate microscopic to the macroscopic B. The current density J is microscopic. The current macroscopic. What was the relation? Relation, if you remember this, the current is current density times A area, then I current. Resistivity and resistance, we just look at it. Resistance equal resistivity times L divided by A, length divided by area. And then finally, this microscopic and macroscopic Ohm's law. Microscopic Ohm's law is current density is electronic field divided by resistivity or law. Macroscopic Ohm's law is current is voltage divided by resistance. And then all these, if you put all these, this relation, put in here, then it becomes here. Or in the other way around, if you put these three relations here, here. So this is macroscopic, looking at the unit area or material as a whole, macroscopic view. Those are the same thing, same Ohm's law. Okay, next. Now we look at electronic power. Voltage V is energy per unit charge. Current is charge per unit time. So if you multiply these two, IV represents energy per unit time. Okay, so this is energy per unit charge, right? And then I is a charge per unit time. So I is a charge, right? So multiply these two, and then that gives you the power of energy. That's we write it P equals I current times V voltage. For materials that obey Ohm's law, V equals IR, so this can be written in different ways. If we put this in, then power is I square R, or power equals V squared divided R. These three are the same law, same relations through Ohm's law. The power and resistance dissipated as here. So if you put the current through something, and then the power is going to be used as a heat. So this is going to be heat out. In other situations, P equal IV may represent electronic energy converted to mechanical energy or other form. So this power, for example, if you have a heater, this power decides how much heat is going to coming out from that in a winter season. If you have a heat electronic, then this power decides how much heat is going to come out. Or for other machines, for example, computer or camera, this power can be used for some mechanical energy in other ways. Electronic safety. So this is one important topic when we're using electricity. Electric current running through the human body is dangerous. Human body is if we go back a little bit, human blood is 0.7, so resistivity, it is a little bit of resistivity, but it's not so huge, so current can go through human body. And then that's going to disturb our heart or muscles, so that's very dangerous. So we should be aware of that. The table below lists the effects of various currents. Much lower current can be dangerous if applied internally. So it takes voltage to drive current through the body. It's a combination of high voltage and the capability to supply at least tens of milliamperes. That's most dangerous. So what you should remember is this 100 milliampere. 100 milliampere body electricity current goes through human body. That's very dangerous because with 100 milliampere, fibrillation of the heart is going to happen and then see death within minutes. So 100 milliampere of the current can disturb your heart's operation. It can stop your heart. So that's why it's going to result in death within a few minutes. So that's very dangerous. So you have to avoid the current over 100 milliampere through human body. And then of course, if you want to put, so human body have some kind of resistance, right? See, resistivity is 0.7. So multiplying the length divided by area is resistivity. So to put this 100 milliamperes of current through human body, you need very high voltage. So it's both combination, the current and then voltage. You have to be careful. Let's look at a bit. It's so, for example, 2 milliampere. 2 milliampere, you feel it. If 2 milliampere goes through down, you feel it. Oops. Usually pain, right? If it goes to 10 milliampere, then muscle contractions. So if 10 milliampere goes through, your muscle against, regardless of your will, start to contract, and then you cannot control it. So this is already dangerous level, and then this 100 is 15 to 100 milliampere severe shock, muscle control loss. Breathing also becomes difficult because you cannot move your muscle to breathe. So these are the numbers you have to be careful. And then maybe you have heard of a taser, this one. Taser. So this is an electronic gun. In, I think, American police, a lot of them use this. So it looks like a gun, and then when you shoot it, these two wires, very, very narrow wires, go through to the target, usually a bad guy, and it hits the bad guy, and as soon as it hits the bad guy, there's a circuit, and then current goes through this circuit. And then it's this taser is adjusted to just to be around here, below 100 milliampere. So it doesn't stop the bad guy's heart, but it shocks it causes the muscle contraction. So this bad guy, if shot with taser, then the bad guy feels the pain, and then it cannot use a muscle, so it just usually falls down. But it doesn't kill the bad guy because it's still below 100 milliampere. So the bad guy's heart is okay. So it just shocks and then stops his motion, but it doesn't kill the bad guy. So it's better option, safer option, I would say, than a gun. Because if you shoot a gun, well, the bad guy might die, right? There's blood and wounds, and the blood might come out. But this just shocks the muscle, and then the bad guy can stop the motion but recover. So it's a safer option. So it's more and more used nowadays. And then this wire can go to like 6 meters, so it can go very far away. For example, like bad guys, is excited at the time. So for example, when they're robbing a bank, and then caught found by the police, and they're excited. But there's no need to kill them, we just need to arrest them, and then they might say sorry, regret it, and then they might become a better person years later. So there's no need to kill them. That's what I think. Okay, then okay, another important thing is this the third one. So when you see the electronic appliances, you sometimes see this third one here sticking out. Do you know what this is for? This is very important. This is to prevent human to get electronic shock and then die. For example, when you're using some electronic appliances, there may be sometimes electricity leak in the appliance or machine. For example, the typical example is when this machine is wet, there's electricity inside. And then human touches. And then because human body, usually legs, touches the ground, then if there's extra electricity here, then current goes through human body to the ground. And that's very dangerous because the current goes through human body. Okay. But if there's a third one, and the third one, usually this third one, there's no electricity going, and there's no current going on, and it's touching the ground, the third one here, third one. So even when there's electricity leaked here, even human touches this thing, the current doesn't go through human body, but the current goes through the third one to the ground. So human body is protected because of this third one. So it's very important to have this third one. And an even nicer thing is usually the modern machines or appliances can sense if there's a current through this third wire, it can fuse this and then cut the electricity from the main power. Then so that, oh, there's a leak, so let's cut it. So that's how it works. So it's even safer. As we saw it, if 100 milliampere of the current goes through human body, you could die. So this is very, very important. So when you see this, please use it. If you see this, you should use it. Okay. That's for your safety. Okay, so here's a summary of what we learned today. Electronic current is the flow of electronic charges. Quantitatively, current flowing through a given area is current is charge dq through unit time dt. The SI, international unit of the current, is ampere A equal to 1 coulomb per second. Current depends on the density M of charge, and then their charge Q and their drift velocity. So you can write it down. Current I equal NQABD. Density, charge, area, and then drift velocity. Current density is the current per unit area. J is NQ velocity. Remember, this is unit area, so there's no A in here. That's current density. Right. Summary continue. Ohm's law, we look at Ohm's law. There's two versions, microscopic and macroscopic version. Microscopic version, the current density J is sigma E electronic field. Macroscopically, voltage is current and resistance. Electronic power is a product of the current and voltage, so the power equals current and voltage. And using Ohm's law, this can also be written. So if you put this in, you can transform it to I square R or B squared divided by R. So both of these are Ohm's law. Okay, so that's the end of today's lecture. Okay, see you next time.